dx? And I did assign that one, right? Did I? Yeah. I don't know. Notice you'd have to complete the square on that one. Oh, actually, yeah, it doesn't factor, so if you wanted to change that in any way, you'd have to do that. I'm not going to try that at first. After all, when I see that ln, my first thought goes to integration by parts. So let's try letting u equal the ln of x squared minus x plus 2, and let's let dv be dx. So du is 2x minus 1 over x squared minus x plus 2, and v is equal to x. So this is uv x ln x squared minus x plus 2. uv minus the integral, u times v minus the integral of v du, so 2x squared minus x over x squared minus x plus 2. Aha, so we see an improper fraction. Or fraction. Pardon me?
X times 2x. Or your...
I did.
Yeah.
Yeah, I multiplied the x through there. That's why it's an x squared now. So that's why it's an improper fraction. The degree of the top needs to be smaller than the degree of the bottom.
Did you divide it by the?
Well, that's what I would do. I would think about that if that were, well, factorable. But that doesn't factor, does it? If you do the discriminant, b squared minus 4 times a times c, you get a negative number. That doesn't. So what am I going to do?
Now complete the square?
Well, I am going to go ahead and do the division because I know that that will at least reduce the numerator. So I'm going to take 2x squared minus x and divide it by x squared minus x plus 2. This is a good technique whether the denominator factors or not. So I'm going to multiply by 2, 2x squared minus 2x plus 4, and then I subtract. So that becomes x minus 4, doesn't it? So I have changed this into x ln x squared minus x plus 2 minus 2 plus the integral of 2 plus x minus 4 over x squared minus x plus 2. So what I've done is I've avoided working with the fraction as long as possible until I could make it as simple as possible. And notice the technique I did worked out well, whether the denominator factors and I can use partial fractions or not, because this is so easy to do now. That's just minus 2x, and I'm subtracting the integral x minus 4 over x squared minus x plus 2. So the question is, what do I do now with that? And I'm glad we finally came across one of these. And one of these is referring to the particular polynomial structure. I wanted to show you an example of how I deal with this. So I'm going to kind of just pull this one little integral off to the side and do that. Whatever we get, we'll just plug it back in and we'll be done. So if somebody were asking you to integrate x minus 4 over x squared minus x plus 2 dx, there's a couple of ways of doing it. The way I'm going to show you now is something that I learned when I was in your place, and I've stuck with it because if you're good at algebra, it works real well. What I really wish in this integral is that the numerator were the derivative of the bottom. If that were a 2x minus 1, I'd let the bottom be u, I'd have du, I'd be done. Well, let's make it a 2x minus 1. So I'm going to multiply by a 2 and a 1/2. So I don't know if you're going to want to pull this trick. You may not like the algebra, but watch how well this works for me. So I get 2x minus 8 over x squared minus x plus 2. Now, I didn't want a 2x minus 8. What did I want? A 2x minus what?
1.
1.
Factor 8.
So, well, factor, I guess you could say that I could have split it up into -1, -7. I'm going to write this as 2x minus 1 over x squared minus x plus 2 dx, well, we love the dx, minus 7 over x squared minus x minus 2. So that one's now real easy. And notice what I've done is it's been a series of steps simplifying the fraction I'm working on, right? I started out with what? There, improper fraction. So I at least made the fraction nicer, made it proper. Then, well, I made the fraction even easier. I went from a linear numerator to a constant. So I know what to do now. Here is u in the denominator. There's du. So this is just going to be an ln. So again, just because I'm trying to illustrate techniques, let's just look at this. Now what am I going to do? Well, this is a particularly ugly one. If I gave you something like this, I would try to give you one upon which we could more easily complete the square. This square is no fun to complete. What number do I need here instead of a -2? Positive 1/4. So I'm going to rewrite this as x squared minus x plus 1/4 minus 5/4. Minus 5/4 plus 1/4 is minus 4/4. Oops. Minus 9/4. Positive 1/4 minus 9/4 is minus 8/4, which is -2. So what I've got now is the integral of 7 dx over x minus 1/2 squared minus 9/4. Now I'm going to factor out the the positive 9/4. So I'm going to have the integral. Look, I wrote it. It's a +2. Sorry. +2. So plus 1/4 and I can't add. So that'd be what then? 7/4 plus 7/4?
You lost your flow.
Well, 7/4 is 1 and 1/4 is 8/4. So that's plus. That's plus 7/4. The 7's cancel, don't they? There's 7 on top, factor out a 7 on the bottom. Well, tell you what, before we do that, let's not be too fast. Let's just factor out the 7/4. That leaves a 4/7, x plus 1/2 quantity squared. Man, I can't do anything right today, can I? And as I said, this is a particularly ugly one because getting 4/7 inside of that square is a decidedly ugly process. So, gosh, I can't imagine giving you one that bad. I would never do that. But this technique is what I wanted to illustrate. I think we ought to abandon this problem and go on to something more useful, especially because I'm almost out of time. So let's see if I can find one that has that technique. This section is where you often come across that. Looks like problem 32 might be one. Oh, but I should be looking at the odds. What factors? 29 doesn't factor. I haven't done 29. Let's do that one. I think I have time for that. And I think that's going to require this technique. I might be wrong, but you wanted 29 anyway, so let's do 29. 29 is the integral of x plus 4 over x squared plus 2x plus 5 dx. So this one is exactly what I was talking about. Notice the denominator does not factor. I wish the numerator were a 2x plus 2. If the numerator were 2x plus 2, it would be the derivative of the denominator. We would be done. So I'm gonna make it a 2x by multiplying and dividing by 2. So I've now got 1/2 the integral of 2x plus 8 over x squared plus 2x plus 5 dx. Now I wanted a 2x plus 2, not a 2x plus 8. So I'm gonna rewrite this as 1/2 the integral of 2x plus 2 over x squared plus 2x plus 5 plus 6 over x squared plus 2x plus 5. So the first integral is now quite easy. You let the denominator be u, du is in the numerator, so that first one becomes 1/2 ln absolute value x squared plus 2x plus 5. You don't actually need the absolute value because x squared plus 2x plus 5 is always positive. 1/2 of 6 is the integral 3 dx over x squared plus 2x plus 5. This is like one I would give you on the exam. Notice the denominator, we can abandon this now and I'm just going to work with that. The denominator square completes rather easily. This will become 3 dx over x squared plus 2x plus 1 plus 4. So integral 3 dx over x plus 1 squared plus 4. Yeah, and we don't even need to get rid of the 4 if you bother to learn that formula I made reference to earlier where they do x squared plus a squared. A is a 2 in this problem. But otherwise, if you don't remember that, you're going to factor out the 4, you're going to factor out the 3. That'll be dx over x plus 1 over 2 squared plus 1. Right, because multiply the 4 back through there, that's a 4, it cancels. You're left with an x plus 1 squared, 4 times 1 is 4. Here you'll make the substitution, t is x plus 1 over 2. So dt, 2 dt is equal to dx. This is 3/4 integral, dx is 2 dt, t squared plus 1. So 3/2, the inverse tan of t, and t is x plus 1 over 2. And of course you're going to add that to the 1/2 ln. You don't need the absolute values, x squared plus 2x plus 5, all plus an arbitrary constant. And good, I'm glad I got one. Whoa, look at that timing. Perfect. You want to make copies of my book? The RFB.